Hi, in this video I want to talk about the power that is being delivered to an inductor, what it does, and ultimately how it gives us a way of determining the energy density in a magnetic field. So if we were to apply Kirchhoff's loop rule to a simple RL DC circuit, we have a battery, we have a resistor, and we have an inductor. Our resistor has a resistance R, our inductor has an inductance L, and the battery's producing an EMF. So there's going to be some current traveling through this circuit. So from Kirchhoff's loop rule, around a loop, our total change in potential difference has to be zero. So we go up through our battery, that means we'd add the EMF of our battery, we're going with the current through our resistor, so it would subtract the current times the resistance, and we're going through our inductor. And with an inductor, the EMF in the inductor is minus the inductance times the derivative of the current with respect to time. So we need to make a point that this current needs to be a function of time, because if it's just constant, that inductor isn't really doing anything important. So our EMF then in our battery would be equal to our current times our resistance plus our inductance times the derivative of our current. Now, in terms of the power for a battery is the EMF times the current. But the power being delivered to the battery has to be going to two places. One, there's the resistor. And any power being dissipated by a resistor is converting that electron motion into heat, and the power being dissipated by a resistor is just the EMF being dropped across that resistor, IR, times the current I, so it would have a resistive heating of I squared R. But there also would be some power element being delivered to that inductor. So multiplying everything by the current, the power element being delivered to the inductor would be equal to our inductance times our current times the derivative of current with respect to time. Well, what that power is doing is transferring energy, and it's energy that's able to be stored using a magnetic field. Well, anytime you're dealing with creating fields, all fields have potential energy associated with them. So if we want to figure out how much energy we store, we can take a look at that power as a function of time and integrate it. So the change in potential energy that we get on our inductor is going to be the integral of the power of the inductor with respect to time. Well, filling in my power, the inductance, which is a constant, times the current, times di dt times dt, well, that differential dt cancels out. And the integral of IDI is a trivial power rule integral. That's going to give me a value of 1/2 I squared times my constant inductance L. So if we take a look at the limits that we have, we're going to start when there's initially no current in the inductor, which means there's no field, all the way up to our maximum current I. So that means then that the change in potential energy acting on that, or stored in that inductor, is going to be 1/2 times the inductance times the current squared. And this is true for any inductor that has a current I passing through it at any moment. There is a magnetic field based on that current, and magnetic fields, like all fields, store energy. So, let's talk about energy density. Say that our inductor happens to be a solenoid, which is a relatively easy shape that we can deal with. Well, for a solenoid, the inductance of a solenoid is mu naught times the number of turns squared divided by the length of the solenoid times the cross-sectional area of our solenoid. Well, I want to rewrite that a little bit by multiplying and dividing by the length of my solenoid. So that would give me the number of turns divided by the length squared as a quantity. And the number of turns per length we use typically with magnetic fields and solenoids as a little n, the number of turns per length. And the area of the solenoid times the length of the solenoid is going to be the volume contained inside that solenoid, the volume in which our magnetic field exists. So the inductance in terms of volume of a solenoid would be mu naught times the number of turns per length squared times the volume of our solenoid. Now, to relate this to magnetic field, we can use the magnetic field equation from a solenoid to figure out what our current would be. The magnetic field from a solenoid is mu naught times the number of turns per length times the current, so our current would just be the magnetic field divided by the permeability of free space mu naught and the number of turns per length. So, if I fill in my value for my inductance, I fill in my value for my current, I have mu naught over mu naught squared. So that's going to give me a 1 over 2 mu naught, and then I have n squared over n squared. That cancels, and I'm just left with the magnetic field squared times the volume. So the energy in a solenoid is the magnetic field squared divided by 2 times mu naught times the volume, and for the energy density, that's just our potential energy divided by our volume, which is our field squared divided by 2 mu naught, which is very similar to the energy density that we talked about when we talked about capacitors and electric fields. The energy density for an electric field was 1/2 times epsilon naught times the strength of our electric field squared. So any field has an energy density associated with it based on that field squared. And as I said, with epsilon naught, it's a measure of how space is able to store energy by creating an electric field. Mu naught is related to how space stores energy in the form of a magnetic field. Thanks for watching.